Hello everybody. In the last session we were discussing about the transformer, and in this session we shall continue our discussion on the transformer, its principles of action and also the features of the device. We shall focus first in this session on an ideal transformer. We were discussing in the last class about the hysteresis loop, and when the operating point traverses around the hysteresis loop, there is some amount of energy that goes unrecovered, and that energy is the loss that happens every cycle called the hysteresis loss. Now, the hysteresis loss we saw was proportional to the frequency of operation and the flux density and also the volume of the core. There is one more type of loss in the core called the eddy current losses. The eddy current losses are occurring by virtue of the Ampere's circuital law that we had discussed, and we saw that if we have a transformer core, let me draw a isometric 3-dimensional view of the transformer core. This is a transformer core. So, the windings are in this pattern. As seen here, and so on. So, this could be the primary, and then you could have the secondary wound in this fashion. So, now we are interested in a cross section of the core as shown here. Now, in this cross section of the core, because there is a primary current flowing, there is a flux which is set up, the magnetomotive force which is set up in a particular direction. Let us say it is in this direction. Now, this magnetomotive force is going to be in a direction which is orthogonal to this cross section area which we have shown hashed, and this, let us say, is the flux. Now, by Ampere's circuital law, if we have a flux or a H field, there is going to be a current in a loop, or if there is a current around the flux, then there will be a flux in a orthogonal area. So, we will be having a current which will be around the like a loop around the flux lines. Now, these currents which I am showing in blue, these currents are called the eddy currents. These are called the eddy currents. These currents are flowing in the solid mass of the core, and as if the mass of the core is highly conductive, then these currents could be quite high, because the resistance will be very low, and the I square loss consequently, because it is dependent on the square of the I, will be very high, quite considerable. And these eddy current losses are not desirable because they are again the energy which is lost and not recoverable and cannot be transferred to the other port, which is the secondary. Therefore, these eddy current losses need to be reduced. So, to reduce the eddy current losses, what is generally done is to increase the resistance of the path where the current can circulate. So, to increase the resistance of the path, what is done is have laminations. What is done is to have laminations like that, so on. Now, these laminations will make the cross section area in such a manner, so they will be like this, the cross section areas, and the currents will flow only in within these areas. So, what basically happen is, for the direction of the current flow here, the rho L by A is reduced. Rho L by A is the resistivity of the material. The resistivity of the material increases because the cross sectional area for the flow of current here is reduced, and the length is also reduced, but still the resistivity is increased. So, once the resistivity increases, the resistance for this cross sectional area for this lamination here will be much higher than for the solid mass, which has a much higher cross section area. Likewise, each of these current loops here, the eddy currents, will see a higher resistance due to the fact that laminations have been introduced, and these will see higher resistivity, and as a result the induced current will be lesser because the induced voltage divided by the resistance is going to be lesser, and as a result the I square losses are going to be contained, much lesser than with a solid mass. So, this way the eddy current losses can be reduced, and that is why in the power transformers you will see that the core is laminated and not one solid piece. Or otherwise, if the core is made up of a highly resistive material like ferrite, then the use of laminations is not warranted. One need not use laminated core. They could use one solid piece of core material because the resistivity of the core material itself is high, which will reduce the eddy current losses. There is an empirical relationship for the eddy current power loss, which is proportional to the flux, maximum flux density square and frequency square. So, higher the frequency, higher is going to be the eddy current losses, and higher the flux density, maximum flux density of the core, higher is also going to be the eddy current losses, because the current that is going to be induced is directly proportional to the flux density, and therefore, you will have the I induced will be also proportional to the amplitude of the flux density, and therefore, the loss is going to be proportional to I square times or Bm square times. So, hence the term square of Bm. So, we have the core losses, which is composed of hysteresis loss, plus the eddy current loss. The hysteresis loss plus the eddy current loss together form the core loss. And as currents are flowing through the copper coil, there is going to be some finite resistance associated with the copper coil, which is wound on the transformer core, the primary and the secondary, and there is going to be an I square or copper loss associated, and that is called the copper loss associated with the copper coil which is wound on the core, due to the fact that there is current flowing through it, and due to the fact that there is a finite resistance associated with the coil, and that is the copper loss. So, core loss plus copper loss will be the total losses in the transformer. Will be the total losses in the transformer P loss. So, if we have a transformer with a primary and a secondary, and if there is a P input, P naught will be equal to P input minus P loss, which is the core losses and the copper loss put together, what comes out here. Now, there is one more important feature in the case of the transformer that we need to be careful about while designing is the volt second balance. The volt second balance, this actually comes from the Faraday's law of electromagnetism. And what does Faraday's law of electromagnetism state? It says that the induced voltage E is equal to N, the number of turns in the core, d phi by dt into d phi by dt, where phi is the flux in the core. That is, if we have a core of N turns winding on the core, and then if we apply a voltage E, there is going to be a flux set up due to the fact that there is a current flowing, and the rate of change of flux into N is going to induce the same voltage E here. Now, this voltage E, which is equal to N d phi by dt, or N AC dB by dt, where phi is equal to B into A, because flux density B is flux by the area of cross section of the core. So, N AC dB by dt, and therefore, the flux is given by 1 by N AC integral of E dt. Now, N and AC are constants, and therefore, B is proportional to integral of E dt. This is the volts and this is the second. That is what is known as the volt second balance, meaning this integrand on integration should not have a waveform that is continually increasing, meaning E should not be a DC value. If E is a DC constant value, on integrating, this would be the constant into T. So, which means it is a continuously increasing value, and after some time the flux density for the particular core, for every core or every type of core material, there is a value of flux density beyond which the flux density will not increase. That is when we say the core is saturated and it loses its electromagnetic property. So, if this value here integral of E dt is continuously increasing, then a time approaches when the value goes beyond the flux density permitted for the core, and the core will saturate, it loses its electromagnetic property and it will just be a plain short circuit. Therefore, it is essential that for that particular core, this volt second integral of E dt is nothing but the area under the voltage curve. The area under the voltage curve should not go beyond a value whatever is permissible for that core, whatever the flux density permissible for the core. This is the volt second balance. If, for example, we have E is a constant, we constant of amplitude V, then integral of V dt is going to be V into T, and this has a ramp waveform, and this keeps on increasing beyond a particular value where we have B sat. Beyond that particular value, the flux core will saturate and it loses its magnetic properties. If E were sinusoidal, Vm sin omega t, then this would result in Vm cos omega t by omega as the this one, and it is divided by omega 2 pi f, and therefore this value has a sinusoidal character, but the peak values are always Vm by omega, and the design value of Vm by omega should be such that this does not exceed B sat of the core. In such a case, the core will not saturate and it will retain its magnetic properties. This is the volt second balance which one need to be conscious about while designing. Now, for sinusoidal waveforms, again from the Faraday's law of electromagnetism, we have E which is equal to N AC dB by dt. Let us draw the BH curve. We have H and B. Let us draw the approximate BH curve. This is the BH curve. Now, you should see that beyond this particular value of flux, this we call it as B sat. Beyond that value of flux, the core saturates. Beyond this value of flux density minus B sat, the core saturates. So, you have to operate at a slightly safer value. Let us say that we do not allow for saturation and that the flux is allowed to swing only between some plus Bm to minus Bm, which is less than B sat. So, then the whole swing of the BH loop is like that. So, that will be the BH loop that will be traversed if the flux within the core were Bm, that is, it swings from minus Bm to plus Bm to minus Bm, so on. Now, going from minus Bm to plus Bm takes half a cycle, and again from plus Bm to minus Bm takes another half a cycle. So, one full cycle means minus Bm to plus Bm to minus Bm is one full cycle. So, let us take any one of the half cycle, which is the flux density swinging from minus Bm to plus Bm or plus Bm to minus Bm in a time span of T by 2. So, we have integral E dt which is equal to n a c b, n a c b, and the B has swung from minus Bm to plus Bm, that is a total swing of 2 Bm in that time, in the time of 0 to T by 2. So, let me multiply throughout by 1 by T by 2 and here also 1 by T by 2. So, this portion is nothing but the average voltage E average across the coil, and this is 2 by T n a c, and the flux that is swung from minus Bm to plus Bm is 2 Bm in a span of T by 2, which is 2 Bm. So, 1 by T is nothing but the frequency. So, we use 2 n a c, this 2 and 2 becomes 4 n a c frequency into Bm. This is E average. We would like to express everything in terms of the effective value or the RMS value. In sinusoidal analysis. Therefore, we use the relationship that we obtained few classes ago when dealing with sinusoidal waveform. The RMS value divided by the average value is 1.11, and therefore, RMS value is equal to 1.11 into average value. So, using that relationship here, if we need to have the RMS value, that will be equal to 1.11 average value, which is equal to 1.11 into 4 n a c f Bm, or we have the voltage across the coil E RMS, which is equal to 4.44 n a c f Bm. This is a pretty important voltage equation for the transformer or the voltage across a coil when we are talking of sinusoids. Now, looking at this equation, the voltage E, if we do not put any subscript here as RMS or average or peak, if a subscript is not used, then it automatically means the effective value or the RMS value is given by 4.44 n a c f Bm. Now, looking at this equation, we see that the voltage that is induced is proportional to the number of turns, and there is the frequency dependence which comes in the frequency of the applied voltage, and this is the maximum allowable flux density. Flux density max allowed. Note here, for various materials, I can give the approximate figures. For ferrite materials, B sat is around 0.3 Tesla. So, Bm should be less than 0.3 Tesla, should be around 0.25 Tesla. For CRGO, this means cold rolled grain oriented silicon steel. B sat is around 1.2 Tesla, and normally Bm is chosen around 1 Tesla, so that it is less than the B sat value and still retains the magnetic properties. For cold rolled non grain oriented CRNGO, cold rolled non grain oriented silicon steel. For this, B sat is around 1 Tesla and Bm is normally chosen around 0.8 to 0.9 Tesla. So, like that, for different materials, different B sat, they are the inherent property of the magnetic material. Different B sats are available, and the operating flux swings, the flux density swing should be less than the B sat value. So, that is the value that has to be used for used in the design equation there. Now, look at a slightly different formation of the equation with this and this brought together on one side. In that case, we have E by F, which is equal to 4.44 N AC Bm. So, for a core, for a transformer design, this is a constant, and once a core is chosen, this is a constant, and once the core is chosen and the number of turns are fixed, the flux density in the core, the maximum operating flux density in the core is also fixed. Then which means this figure is a constant. This voltage by F, V by F, E by F being a constant also means or implies that volt second is a constant. So, one has to design for a volt second product in the case of the transformer such that the flux in the core does not exceed, the maximum flux density in the core Bm does not exceed B sat for that core. That is the important conclusion that you should draw from this particular modified equation here. Now, we have the transformer, and we have been representing this transformer in this fashion. That is, we draw a square core, and then we have the windings, which are written like that. This is the primary and this is the secondary. This is N1 number of turns, this is N2 number of turns, NP number of turns or NS number of turns depending upon. Now, we shall represent this as an electrical symbol. We have an electrical symbol associated with this, which will be used in all the circuit diagrams. That is, it is written in this form. There are two coils like that, and then there are two parallel lines which are drawn in between to show that these two are coupled with a core inside in between. This is the primary or E1, this is the secondary or E2, there is a primary current or I1, secondary current or I2. This is the, and there is a N1 is to N2, number of turns in the primary, number of turns in the secondary. This is how a transformer is represented as a component in an electrical circuit. Now, here we have less number of turns here and more number of turns on the secondary side. This would in general imply that the primary voltage is smaller and the secondary voltage is larger, and it is a step up transformer. That would be a step up transformer. If the symbol is written in this fashion, as shown here, with the primary voltage more than the secondary voltage, and consequently the primary number of turns being more than the secondary number of turns. Now, here you have N1 less than N2, and here you have N1 greater than N2. So, which means E2, the secondary voltage, is less than the primary voltage, and such a transformer is called a step down transformer. Step down transformer. And if one writes symbol with equal number of turns as shown here, then such a transformer is a 1:1 transformer. This is the primary E1, this is the secondary E2, the primary current I1, secondary current I2. This is a 1:1 transformer. The secondary voltage E2 is the same as the secondary current, primary voltage E1. The main function here is that galvanically the primary portion of the circuit and the secondary portion of the circuit are isolated, meaning there is absolutely no contact between the primary portion of the circuit and the secondary portion of the circuit. For such applications where one uses a transformer just for the purpose of isolation, galvanic isolation between one part of the circuit and another part of the circuit, then such a transformer is called a isolation transformer. Of course, a transformer can be used to perform more than one of these functions, like it could be used for performing isolation plus step up, isolation plus step down, so on and so forth. Now, to complete the symbolic representation of the transformer in the electric circuits, there is one more item that we need to add, and that is we have the primary winding, secondary winding. They have two terminals here, we have two terminals here. Let us say this is E1 and this is E2, and we have a core in between. This is N1 is to N2. We also add a dot. So, this dot indicates that at the dot end the polarities on the two sides of the transformer, that the primary side and the secondary side, are in phase. That is, if the voltage is measured at this point with respect to the non-dot terminal, and likewise on the secondary side the voltage measured at the dotted terminal with respect to the non-dotted terminal, the voltages will be in phase. We have a transformer this fashion, and let me put the dots like this, and let us call this terminal as A and this terminal as B, this terminal as C and this terminal as D. Now, we are going to apply, let us say, some voltage across the terminal VAB. We now apply a voltage across the terminal VAB. It is an AC voltage. Now, how does the waveforms look across the primary and the secondary with respect to time? Let us say VAB, meaning we are measuring at A with respect to B, and the other one is VCD. We are measuring at C with respect to D. And so, if we had a waveform of this sort across VAB, which is applied, then the voltage VCD will be in phase, as shown. Now, if we have a dot polarity of this fashion, which depends upon the winding sense. So, instead of winding the secondary, let us say, which was clockwise in the previous case, it now becomes anti-clockwise. The dot polarity is now in this form. So, therefore, the secondary is no longer, VCD is no longer like the case that we saw before. It is now so when A is positive with respect to B, it means that the dot portion will be positive with respect to the non-dot portion. So, if A is positive with respect to B, D will be positive with respect to C. So, in VCD, C will be negative with respect to D. So, we would see that there is a reversal of polarity. And when A is going negative with respect to B, D is also going negative with respect to C, but C, if D goes negative with respect to C, C goes positive with respect to D, and that is what is happening. CD is positive during this time. So, you see that there is a 180 degrees phase reversal. So, dot polarities are crucial to indicate the phase relationship between the primary and the secondary. So, the phase relationship between the primary and the secondary are represented by the dots called the dot polarity. So, the dotted portions are supposed to be in phase. And now, these dot polarities can also be used for generating the phasor relationship to get the phasor diagram between the various parts of the circuit, including the transformer. Let us draw the phasor relationship between the primaries and the secondary for any given dot polarity. So, let us have a primary coil, let us have a secondary coil, there is a core, and there is a primary. We will keep it as E1, consistent with the other. There is a primary voltage E1 and there is a secondary voltage E2. As of now, there is no load connected here. So, let us now do that job of connecting a load across the secondary. This means there is going to be a current I1, there is going to be a current I2 in the secondary, and this is N1 is to N2. Now, let us also have the dot polarities like that. So, which means when the dot side is positive, the dot side here is also positive. Note that here when the dot side is positive on the primary side, this is the secondary, the current is entering the dot, and here the current is leaving the dot. When the current is entering the dot and this is positive, energy is put into the transformer. The dot side is positive, current is leaving the dot, energy is removed from the transformer. So, that is how the energy passes through the transformer and goes from the primary to the secondary side. Now, let us represent this as our conventional winding that we used to do before with a rectangular core. Let us say we have a core as shown here. There are some windings. So, we have the primary side winding, we also have the secondary side winding, we are going to connect a source, an AC source of frequency f across the primary, which is going to result in voltage E1. So, the applied and the induced are going to balance each other, and there is going to be a load resistance or an impedance here, which is going to result in E2. Let us say that I mark the generated voltage and let me call that one as EG. Under normal conditions, EG will be same as E1. Now, let us say there is an I1 and now there is an I2 flowing through the load. This has N1 number of turns and this has N2 number of turns. Okay. So, this current I1 flowing through N1, initially when the load was not there, let us say initially load was not there, this is open, which means I2 is 0. So, the current flowing through N1 generates a flux due to the ampere turns Ni. And let us say this is N1 I1. Now, if the load is connected and this flux N1 I1 which is generated in the primary is linking the secondary and multiplied by N2, a voltage E2 is generated by the Faraday's law of electromagnetism. And the moment you connect the load here, E2 divided by whatever the impedance Z2 is going to result in a current flowing through the secondary circuit. Now, this current is flowing through this coil, which is going to provide a cancelling motive force. So, MMF is provided here plus minus, let us say here at a given instant. Now, a current flowing out of the dot, isn't it? Let me put the dot. The current is entering the dot, current is flowing out of the dot, is going to create a cancelling MMF. So, what happens? We are going to have an MMF which will cancel the earlier MMF, and this is N2 I2. And due to the cancelling effect, the MMF is reduced. A reduction in the MMF means on this side the induced EMF E1 has reduced, but the applied voltage EG is still the same. The EMF here E1 instead of being same as EG has now reduced, which means there is a voltage potential difference which will cause a very high current to flow. So, the current will keep on increasing till the current I here goes back, balances the cancellation due to this. So, the current I1 here will increase till N1 I1 balances the cancellation due to I2, N2 I2 that occurred due to the presence of the load. So, which means I1 would have increased such that E1 now matches EG. So, this would mean that there is a cancelling MMF provided by the primary N1 I1 dash such that this is cancelled out. And what will remain would be N1 I1 under the case when there was no load, and that would be the magnetizing component of the flux. So, the flux in the core is going to be same as it was under no load condition. Whatever may be the load you may increase, there will always be a cancelling ampere turns that gets generated in the primary, which will cancel out the load induced ampere turns, and thereby the flux in the core is always going to be constant whether it is no load or loaded condition, such that the volt circuit balance is maintained according to the previous equations that we saw, which will make the transformer to operate in the magnetic zone. Now, with this concept, now we should be able to draw the phasor diagram. So, we have here the primary, and the primary is connected to a source, voltage source. I will still name it as EG as the generated voltage or the applied voltage. This is the generator voltage which is applied, and there is a induced voltage across the primary. Effectively E1 equals EG always at every instant of time. However, to distinguish between the generator voltage and the induced EMF or the induced voltage, let us have this distinction. And we have a core and then the secondary, and the secondary is connected to a load, and the load could be resistive or RL or RC or RLC, any impedance Z2. Now, there is a voltage across the secondary and we call that as E2. Now, the current through the primary we will call it as I1, current through the secondary we will call it as I2. We have the dot polarities as shown here, and this is N1 is to N2. This will complete the way the transformer looks. Now, let us draw the phasor diagram for this transformer circuit. This is the spatial coordinate systems, as I have been saying. We have seen quite a few times in the earlier classes or earlier sessions while discussing the phasor diagrams with sinusoids. This is the alpha axis and this is the beta axis. So, we need to choose some reference phasor along this direction, and remember that phasor means same as the vectors, except that the amplitudes are effective values or the RMS values. Now, we shall choose the input voltage as the reference direction, that is, this would be the EG direction that we are choosing. Now, as EG and E1 are one and the same, this also means that we have E1. in phase with E g. Now, by the dot polarities, let us say N 2 is, for the moment, N 2 is less than N 1, which means it is a step down, E 2 is less than E 1. From the dot polarities, we say that E 2 and E 1 are in phase, exactly, they follow each other by the dot polarities, which means E 2 is in phase with E 1. Now, let us say that Z 2 is a lagging power factor load, that is an inductive load, which means I 2 has to lag E 2. So, let us have I 2 lagging E 2 by some angle theta. What happens to I 1? Now, we see that N 2 is less than N 1. We know that E 2 by E 1 equals N 2 by N 1. So, E 2 is N 2 by N 1 into E 1, which is less than E 1, and I 1 by I 2 equals N 2 by N 1. This is the inverse proportionality. So, N 2 by N 1 is less into I 2, sorry, this is, yeah, N 2 by N 1 is also equal to I 1 by I 2. So, N 2 by N 1 is less, and therefore, I 1 will be less than I 2, whatever the value of I 2. So, I 1 will be less than I 2 in this case, E 2 will be less than E 1 in this case. So, which means we will have I 1 here, because by dot polarity I 1 and I 2 will be in phase, because E 1 and E 2 are in phase. So, I 1 will have a vector in phase with I 2. Now, what about the flux in the core? So, the flux in the core will be lagging the voltage by 90 degrees. This is the flux phi m in the core. This is because we have V which is equal to N d phi by dt. There is a d phi coming, which is N j phi m. So, we see that the voltage vector is whatever the phi m vector direction rotated by 90 degrees because of the j, and that is what it is, that is what it means by this j operator. So, phi m should lag voltage by 90 degrees, that is what it means. So, this would be the vector diagram of an ideal transformer. In the next class, we will see how a practical transformer will behave after having done few examples, some examples in this case.